Dear students, we were discussing about different types of stresses. Yesterday we have seen tensile stress, compressive stress, and also we have touched a little about the bending stress. Bending stress is given by the bending equation. This is the bending equation. M upon I is equal to sigma B by Y is equal to E by R. And this can be rearranged as sigma B. If you take these two terms together, sigma B is equal to M into Y divided by I. Otherwise, it can be written as M upon I by Y, where M is the bending moment, I is the moment of inertia, and Y is the distance of the extreme fiber from the neutral axis. And in further later on we will see that is this I by Y, this term is replaced by a term called Z, a section modulus. So sigma B, that is bending stress, will become M by Z, that is bending moment upon section modulus. So this is the formula. Yeah. So the maximum bending stress induced at the outer fiber, you see if this bar is made of so many fibers, one fiber, two fiber, one below the other, there are many fibers, then the fiber that is at the center will not be experiencing any bending stress, because you see here, as it is depicted here, from the center towards the outer fiber, the stress goes on increasing. On one side tension, the other side compression. So now what is bending stress? Is it tensile stress or compressive stress? Bending stress can be either of these. See, actually bending stress is a direct stress. It is either tension or compression, because some fibers will be experiencing tension, some other fibers will be experiencing compression. So the extreme fiber will have the maximum bending stress, and the fibers towards the neutral axis will be experiencing lesser bending stress. So that's why on the extreme fiber sigma B max is written, that is bending stress maximum. Okay, so now what is the formula that we are going to use? This is the formula that we are going to use. Sigma B is equal to M by Z, where Z is called the section modulus given by I by Y. Okay, as this terminology, M is bending moment at section XX, and sigma B is the bending stress at a distance Y from neutral axis. Sigma B, see, when we are designing, we have to design for maximum stress. When a component can withstand maximum stress, it can as well withstand lesser stresses. So if it fails, it will fail at the maximum stress point. Okay, so this is the maximum stress. If we are taking Y to be the distance to the extreme fiber will have maximum stress, and we need not bother about the internal fibers because they will have less stress only. So failure will not happen there. If the component will fail, or if it gets some cracks, or it gets damaged or something, the damage of crack will initiate at the extreme fiber. Okay, so and then I is the moment of inertia. So this is the formula we'll be using. We'll be dealing with bending stress further when we solve some problems. Okay, next come to the shear stress. Now shear stress is we have seen that it can be a direct shear stress, which is called a transverse shear stress, and the other is called as torsional shear stress. First let us see direct shear stress, which is simple to understand. Okay, see here you see a riveted joint given. Last year you may in drawing you may have drawn this conventional representation. If this is one plate, this is another plate, and you drill a hole between that and insert a rivet, and then with the help of riveter you make the other end also to be made into a cup. Then this riveted joint is ready. Okay, so this is called if you see now in this figure, if force is applied uh, as shown here, so that means this plate is being pulled to the right and this plate is being pulled to the left. Then what will happen? You see, if the force keeps on increasing at one stage, what will happen? You see, here this rivet in the center may cut off. That means shear off, and this joint may fail. Fail means break into two. As it is shown in the figure here, the rivet may cut in the middle, that is shear off in the middle, and the joint will fail. Okay, such a thing is called as shear failure. So here the definition: when a component is subjected to two equal and opposite forces acting tangentially. See, it is not coming directly vertically like this. See, it is acting tangentially across the resisting area. It is the result of a result is it results in shearing off of the section. The stress induced in such a section is known as direct shear or transverse shear. Because the force is transverse, it is called as transverse shear. Okay, again in this I think you understand what is shear stress. Now let us go to further classification within the direct shear, the transverse shear. There are two types. One is single shear and another is double shear. Single shear means in this figure you see this rivet is getting cut in one place only. So that is simple. That is called single shear. Okay, and the formula, see, shear stresses are given by this letter tau. This is a Greek letter tau. You know how tau should be written. Okay, and the suffix d means it is a direct shear direct shear stress is equal to load upon area. Again the formula is same, the same formula that we used for tensile stress, load upon area. The same formula we have used for compressive stress, load upon area, and we are using the same formula for direct shear as well, that is load upon area. Okay, so what is P here? P is the direct shear force acting on the section. And what is area? Area is the cross-sectional area of the rivet. Okay, it is given in millimeter square or meter square. So the formula will become tau d is equal to P by A, and this tau d will have units Newton per mm square. That is the shear stress formula. That is the units of stress. Okay, and in case of double shear, what happens? You see, suppose in case of knuckle joint or something, or in case of double riveted joint, what you see is, if a joint is like this, if rivet is inserted into a fork or double eye like this, and there is in the center a single eye, and if you are pulling the single eye this side and the double eye the other side, what will happen is it may cut off in two places, here also and here also. So in two places you can see as it is represented here, double shear, it fails up and down. Okay, so now what will be the formula? Here it not only has to tear off here, it has to tear off here also. Therefore here tau d, it should be d, is equal to P upon 2a, because 2a means twice the area, cross sectional area. Now coming to the next stress, second second type of shear stress is torsional shear stress. This torsional shear stress we experience. You see, suppose there is one circular bar protruding from a wall or something, and this bar towards the end is subjected to some twisting um, torque, twisting moment. Then if you are, that means, you know, this is represented by this capital T. Okay, if you are, you see, if you take, if somebody's hand you hold at the end and try to twist it, you see what happens, it will be twisted near the support. Okay, from the support, you see, that means what, in the towards the support there will be less twist, and as you go far away from the support, there's a twist, you know, the distance here will be increasing. So this angle by which it is being twisted is called as the twisting angle. Okay, so what is the definition here written? When a machine member is subjected to the action of two equal and opposite forces, that is called couple. Couple means two, acting in parallel plane, or torque or twisting, then the machine component is subjected to torsion. Okay, you just imagine, if you keep on twisting with great force, what will happen? At some time, at some point, when the when with more torque, if you are twisting it, it will break. Okay, such kind of failure is called as torsional failure, and the stress in this is called as torsional shear stress. Okay, so stress developed in element is torsional shear stress. It is zero at the centroid axis and a maximum at the outer surface. See, as it is obvious, it is pictorially represented in the side view like this. If this is the diameter of this circular cylindrical rod, and then if you plot the shear stress, it will be zero at the center, and as you move out towards the circumference, the shear stress, the torsional shear stress increases. Okay, now let us come here. What is the formula that we use when we are computing the shear stress? Let a component of circular cross section subjected to torque T. You see, what is T? T is this one. This is the torque T, and this is the diameter D, and this is the length of the rod L. These three parameters are here. Okay, now there is a formula similar to bending equation. Here we are having another equation which is called as torsional equation, torsion equation. Okay, see, the torsional shear stress induced by the at any fiber is given by the torsional equation. See, the torsion equation is tau upon r. What is r? R is radial distance of the fiber from the neutral axis or the centroidal axis. So that is d by 2. You see here, what is r here? You see, d is equal to 2r. So r is d by 2. Okay. So tau upon r is equal to T upon IP. T, this is the torque or the twisting moment. The units of this is Newton millimeter. You see, the twisting moment is normally given by the force that is applied and the distance, F into L. Okay, this is how the torque is given, because load has Newton unit and distance has millimeter unit. So the units of torque become Newton millimeter. What is the unit of R? R will be in millimeter. Okay, and what is IP? IP is the polar moment of inertia. This moment of inertia you must have studied in applied mechanics. Not here. Now we are not going to derive all those things. We just use the formula. IP is the polar moment of inertia of the cross section about the centroidal axis. So this polar moment of inertia has the unit mm to the power 4. So on the top is T, Newton per millimeter, bottom is millimeter to the power 4. So here the units are, this is millimeter, this is this is Newton per millimeter square, and this is millimeter. So therefore this becomes Newton upon millimeter cube, this term. Similarly, this also 1 mm gets cancelled, and this also becomes Newton per millimeter cube. Okay, and now next term, third term, is g theta upon L. What is g? G is the modulus of rigidity. And what is theta? Theta is the angle of twist. And what is L? L is the length of the component under torque. Okay, and from again this all these things, no, you see what is modulus of rigidity's unit? This under stress have same unit, that is Newton per millimeter square. Theta has no unit, and this has millimeter. So this term also becomes, see all these terms, then only we can equate them. This comes Newton upon millimeter cube, this one comes Newton upon millimeter cube, and this term also comes upon comes as, the units come as Newton upon millimeter cube. Okay, now from this equation we can deduce, if we taking the first terms alone. Now at present we don't need the third term. Okay, tau is equal to torque into radius upon polar moment of inertia. Okay, and when we are designing in machine design, the maximum value of the torsional shear stress, which will be occurring at the outermost fiber. You see, at the innermost fiber, stress is 0. As you move towards the outer fiber, it will be maximum. So at the maximum fiber, their R is d by 2. So let us see for the circular section. So for circular section, we have Ixx is pi d to the power 4 upon 64. Iyy is pi d to the power 4 upon 64, and polar moment of inertia is addition of these two, that is Ixx plus Iyy. You see, x-axis is the moment of inertia about this axis, y is this axis, so Iyy is the moment of inertia about this axis, and polar moment of inertia is the summation of these two. This is pi d to the power 4 upon 32, whereas R maximum is d by 2. Okay, if we substitute in these things in this formula, then we will be able to solve this. Okay, that when we are solving the problems, the idea will be more clear. Okay, coming to the next stress, there are two stresses which are called bearing pressure and bearing pressure and crushing stress. So here one is bearing pressure. First, bearing pressure. This pressure, bearing pressure, bearing pressure, how it is defined. See, all the other stresses are body stresses, and now this stress is a localized stress. Localized means what? Is if you are touching the surface, only on the surface, where is the area of contact is there, only there you will have the stress. So that is a localized stress. See, on the seat you are sitting, then that surface only will experience stress, not the inside of the metal. Okay, so like that, wherever is the contact, if you are tightening bolt or something, so wherever the bolt or the washer are touching the surface, there only the stress is experienced. Such a stress is called as localized stress. If it is there in the entire body, like in case of tensile stress, it is called body stress. Okay, we'll discuss in the next